Stars are being observed at an unprecedented rate through projects such as the Sloan Digital Sky Survey, the Large Sky Area Multi-Object Fiber Spectroscopic Telescope, and others. A challenge faced by modern-day astronomers is sifting through the data collected on millions of these observed stars. My name is Derek Shank, and I worked under the Data-Intensive Scientific Computing REU at the University of Notre Dame, solving the problem of analyzing large-scale astronomical data. Astronomers are interested in physical properties of a star which can be derived from the spectra collected through the surveys mentioned earlier. These properties include the effective temperature of a star, the surface gravity of a star, the metallicity of a star, and the carbon abundance of a star. Depending on the properties these stars possess, astronomers can then closely analyze a star which meets their criteria. One of the tools used in determining the physical properties of stars is a data-driven analysis program called the Canon. While not an actual canon, the canon works by analyzing a set of reference spectra with known stellar properties which have little to no noise throughout the spectrum. Then, by fitting a flexible model at every wavelength, the canon constructs a probability density function at each wavelength as a function of the known stellar parameters. The test set of spectra with unknown stellar properties is then fed into the canon, and it attempts to accurately predict the stellar properties of the star. For calibration of the canon, idealized synthetic spectra from a spectral library were used as the reference set with temperature, surface gravity, and metallicity being the known stellar properties. The test set also consisted of synthetic spectra from the same spectral library and were used as a proof of concept for the power of the canon. As you can see for the temperature, the canon is able to accurately predict the temperatures in the test set. The surface gravity of the star is not as well defined as the temperature, but the results are promising. The metallicity of the star is well defined for the higher metallicities, but starts to become less well defined as the metallicity reaches -3.5. In future work, the canon will be applied to observe spectra and used to analyze stellar properties for stars. Other tools exist, such as the non-segue stellar parameter pipeline, to predict a star's properties, and can be used to compare predicted values with the canon's predictions. Being able to compare stellar properties allows researchers to only manually check the stars which do not have the same predicted properties.